I welcome you to this class of microscale transport process. What we have been discussing is dispersion, more importantly the Taylor dispersion. The dispersion that we have been talking about is what we have done in the last class. We have discussed about a slug or a pulse that is going into the tube, which is through which the laminar flow is taking place. That means, there is a parabolic velocity distribution already developed and you are introducing a small slug. So, what we studied at that time is the deformation of the slug because of this parabolic velocity distribution, because the central portion of the tube would be flowing faster, that will have a higher velocity, whereas the layer that is adjacent to the wall, that would be moving at a slower rate, or next to the wall it would be at the wall the velocity is 0. So, you have the flow taking place in a parabolic manner. So, that there would be this slug will be deformed. So, that is the hatched portion that we have discussed in the last class. So, this slug would be deformed. So, when you collect this at the outlet, mind it that this dimension is very small here, and this type of dispersion is important when the dimension is small actually. So, what you collect at the outlet is basically if you collect them layer by layer, that means what you collect is the average over the entire cross section, and then the next block that arrives, and then the next block that arrives. And if you find the average concentration of this layer, then the next one that arrives, the average concentration, that means at any point you are finding the average over the entire cross section. So, some part would be higher concentration of solute because of this deformed pulse, and the other part will have no solute, because there was not any. So, this layer is moving at a slower rate. So, if you plot the concentration at the detector means the concentration average concentration of this block that is detected by the detector, which is positioned at the outlet. There, if you plot the concentration detected as a function of time, what you see is a distribution, because the first layer will have some concentration, then there would be some concentration, then there would be some other concentration. What ideally you had expected is that you have introduced a pulse. Pulse is like this, or if you are looking at a Dirac function type pulse, then it would be practically high value at 0, and then rest of the places it is all 0. So, this is the type of pulse you are looking at, but at the outlet you are seeing a pulse which has a distribution, and this is what we are referring as Taylor dispersion. And at the very outset I said that this concentration, if somebody tries to express this C1 bar is the average concentration over this entire cross section for a particular layer, that as a function of z and t. What does this mean? Z is the length after which you are collecting it, okay, and t is the time. So, as a function of z and t, you would be getting this concentration. You have this kind of functionality, and I told you at that time that this functionality has something in common to what we have already discussed before. When we talked about diffusion of a spot of tracer in an infinite medium, we had a very similar expression that time. Okay. However, there instead of Ez we had the diffusivity term, and instead of z minus V0 t, I think we have just we have some dimension of length there. Here this z minus V0 t is, I mean, it must be obvious to you that you are trying to put together a moving coordinate system. V naught t is the distance that the pulse would have moved at an average velocity V0 in time t. So, this z minus V0 t is an offshoot of going to a moving coordinate system, and this Ez is equivalent to diffusivity. Now, we are trying to write down at least the governing equations that leads to this expression. However, I would like, I have already pointed out to you that these Ez, which we are referring as dispersion coefficient, which is the term equivalent to diffusion coefficient in case of a diffusion of a spot of dye in an infinite medium. Now, this Ez, this time we are calling it a dispersion coefficient, and the expression for this dispersion coefficient, here I see that d, the diffusion coefficient or diffusivity, that is appearing in the denominator. On the other hand, in the numerator you have R 0 V 0. So, this is this dependence is completely I mean it inversely depends on D, whereas you expected this to be equivalent to the diffusivity term. If it is equivalent to the diffusivity term, then D should have been in the numerator, but instead of that D has gone to the denominator. So, that is the interesting part of it. So, what this means is, if something has a higher diffusivity, if something diffuses very fast in the liquid, then you expected that then probably that the spreading would be more, but in case of a Taylor dispersion the spreading would be less in that case. Okay. On the other hand, if something is flowing at a high velocity, that can contribute in a major way to the dispersion. So, this is what I have given you at that time, and then what I have done is I have written down, I mean I have tried to put down these governing equation. We pick up a differential element. If capital R is the radius of the tube, then you pick up a differential element which has a dimension. I mean you pick up a differential element of this it is an annular shaped element. So, this annulus is basically between R and R plus dr. So, this annulus we are talking about, and it has a depth of delta z. So, if you try to write down the differential equation, or if you try to write down the governing equation for concentration, I mean this we discussed in the last class, that you would be writing an equation something like this, and then you have basically what you are accounting here is the convection in the axial direction, that means convection in the z direction, and diffusion in the radial direction, that is what you are looking at. Okay. So, del C1 del T is equal to this. So, this is the final equation that we arrived at, right. This is the result of diffusive term, that means radial diffusion, and this is the result of convective term. Convective term in a sense that this part 2 V 0 into 1 minus R by R 0 whole square, this term is basically the velocity, local velocity, and that V del C1 del Z, this is the convective term. So, V naught is the average velocity, and 2 V naught is the maximum velocity, and this you know it comes from a standard expression for parabolic velocity profile. So, this is the governing equation, and at that time I pointed out to you that the initial condition is at t equal to 0 for all r, this concentration is given as m by pi r 0 squared delta z. That means, you are assuming that at time t is equal to 0, you are introducing at t equal to 0, you are introducing at the inlet a Dirac function. I mean you are introducing a spot of tracer at the inlet, that is applicable to all r, and then at t greater than 0, for t greater than 0, you have assumed that at r is equal to 0, del C1 del r equal to 0, which arises from symmetry, and at r is equal to r 0, that means at the wall this del C1 del r is equal to 0, which is arising from no flow or no diffusion, no diffusive flow. Okay, no diffusive flow. That means at the wall there isn't any diffusion taking place. So, d del C1 del r, that has to be equal to 0, or in other words del C1 del r equal to 0, and at r is equal to 0, whatever profile you have that has a symmetry at the symmetry along that central axis. So, that has to be honored. So, r equal to 0, del C1 del r is equal to 0. So, these are the boundary conditions that you have for all t greater than 0. Then you have introduced two dimensionless quantity, one is eta, which is equal to r by r 0, that means dimensionless radius, and another is dimensionless axial distance, which what you have done is, here you have written zeta is equal to z minus v 0 t by r 0. Z minus v 0 t is arising from the moving coordinate, that means this entire spot is moving at an average velocity v 0. So, you are accounting for that. So, this is what you have at that time, and I said in the last class that this is a solution for the differential equation d by eta. This is a solution that satisfies the governing equation as well as the boundary conditions. Okay, and no, first of all, okay, this is the converted form. Okay, the first expression that I put here is the governing equation in terms of eta and zeta. Instead of writing it in terms of r and z, it is written in terms of eta and zeta, and then we said that this is one solution to this equation. And then then what we discussed in the last class is that C1 bar z, that means that is what we are trying to find out, the concentration averaged over the entire cross section. So, if you try to find out the concentration averaged over the entire cross section, you have to pick up a differential element, annular shaped differential element, find out what is the concentration. So, for that annular shaped element, the concentration is C1 R Z. For that annulus whose inner radius is r and the outer radius is r plus dr, for that annulus the concentration you assumed is C1 R Z. That means, the area over which this concentration applies is 2 pi r C1 R Z. So, 2 pi r dr, if you have an annulus you are talking about. Okay. So, this is r and this is dr. So, you are talking about this. So, ideally this should be what? This should be pi r plus dr whole square minus pi r square, that is the area of this annulus. And if you ignore this dr whole square term, if you ignore this dr whole square term with the assumption that dr is small, then you can write this expression is equal to 2 pi r dr. So, that is the area of this annulus. So, you are multiplying this area, annulus area, with the corresponding concentration, and you are integrating all such products from 0 to r 0, and then finally you are dividing by the entire area of the circle, pi r 0 square. So, that is how you are getting the average concentration, which is C1 bar z. All right. So, this C1 bar z is equal to 2 into integration 0 to 1 eta C1 d eta. All right. So, this is what you get as C1 bar. Now, here you make an assumption. The assumption is like this. The assumption is like this, that you are assuming del C1 del zeta, that is equal to del C1 bar del zeta. This is an assumption you make at this point, because this will help treating del C1 del zeta as independent of r. So, this is the advantage that you want to make, that is the advantage that you want to take, and to take this advantage, what you write here is del C1 del zeta is equal to del C1 bar del zeta. What does this mean? I mean, do you have much of an idea what this could be? Zeta is already in moving coordinate. So, at a particular zeta is already in terms of moving coordinate. So, the change in concentration in direction zeta can be expressed as change in the average concentration with reference to zeta. That is what you are making here. So, this is with this assumption, what you can write in this case is that your then in that case you can write this as del C1 bar del T is equal to minus del G1 del of zeta r 0, where G1 is the averaged flux with reference to moving coordinate, that means is equal to 1 by pi r 0 square integration 0 to r 0 2 pi r V z minus V 0 C1 dr, okay, which happens to be equal to, I mean, let me give you the final expression first, 4 V0 integration 0 to 1 eta into half minus eta square C1 d eta. This is the final expression. Okay, so what you have here is that, so what you are having here is you are basically solving this equation. Instead of writing it in terms of C alone, you are writing it in terms of C1 bar. Okay, and since you are writing in terms of C1 bar, this J1 that also has to be averaged, and this is how the J1 would be averaged in that case. Okay. So, what you do here is you would be writing this as this expression. First of all, this expression will take the shape del C1 bar, and instead of del T you club some of the terms, because you are bringing these. So, when you are, this J1 would be replaced by this whole thing, you have this J1 would be replaced by this expression that you have. Okay. So, this J1 would be replaced by this term here. So, what you do here is, instead of del T you write del T V0 by R0 and call this tau. Okay. This is equal to minus del of J1 by V0 del zeta. It is nothing. I mean, you have divided. See, here you have included a V0 and R0, which would be, which has already, this R0 was coming from here and this V0 has been added here. So, this is how you are doing it. So, this left hand side you are calling it, this left hand side you are calling it del C1 bar del tau, because tau is this quantity T V0 by R0, this quantity is called tau. So, del C1 bar del tau, and this is equal to, on the right hand side you have to replace this J1 by this quantity. So, what you would end up with is V naught R naught by 48 d del square C1 bar del zeta square. Okay, so this is the expression that you will have in that case, and this expression will have, now you will impose those initial and the boundary conditions. The initial condition is that at tau is equal to 0 for all zeta, C1 bar is equal to m by pi r0 square delta zeta, and for tau greater than 0, zeta is equal to infinity, C1 bar is equal to 0. So, with that you will solve this equation. So, then it would be this term can be simply replaced. This is in fact the Ez term that you have looked into. So, this treatment would be very similar. So, the treatment would be very similar to the one that you had for diffusion of a spot of dye in an infinite medium. Instead of d you have this Ez term appearing, and so you have the solution which we had earlier. We have written it earlier, that m by pi r0 square divided by square root of 4 pi Ez t e to the power minus of z minus V0 t whole square divided by 4 Ez t. So, this is the term that you had. We have already seen this expression before, but now at least we have identified the governing equations and the boundary conditions that are leading to this expression. Okay. Once again I point out that for this expression you have m is equal to total solute in the pulse R0 is equal to tube's radius Z is equal to distance along the length of the tube V naught is equal to fluid velocity, T is equal to time, and E z is equal to dispersion, E z is equal to dispersion coefficient that is equal to R 0 V 0 square divided by 48 d. This is considered equivalent to Peclet number for Taylor dispersion. Peclet number for Taylor's dispersion. So, these are the terms that you have, and with that this is the expression that you had, we have written it already. This expression I have pointed out before that this expression this has all the inherent features of a diffusion of a spot of dye in an infinite medium, but what you needed to do at this here, I mean if we try to quickly recap on what we have done, we made an assumption here that del C 1 del zeta is equal to del C 1 bar del zeta. That means, the change in concentration in the z axis when you are considering you are with the moving coordinate system, that you are treating as same as the change in average concentration in the same zeta axis. So, by doing this, what you are doing is del C 1 del zeta has become independent of R. So, that feature you are taking into account, and then you are writing that basic governing equation, that del C 1 bar del T is equal to this quantity minus del J 1 del zeta R 0. This is how, so this becomes your governing equation, I should say, in terms of C 1 bar. Now, you are talking about a diffusion, you are talking about the change of C 1 bar with T, and why C 1 bar is changing. I mean, think of it, I mean now we do not have the dependence of radial direction. So, radial part is completely taken off. The moment, so this is the advantage of this condition. You have written del C 1 del zeta is similar to del C 1 bar del zeta. Moment you write this, then what you would be doing is you would be doing your entire analysis in terms of C 1 bar, and this radial axis is completely gone. You have already incorporated whatever you are supposed to do in the radial direction, and now you are talking about the average concentration over the entire cross section, and now that average concentration over the entire cross section, that is changing with time, and that is changing with time because there is convective flux in axial direction, that means in z direction, and that convective flux, so that is expressed here del J 1 del J 1 del zeta R 0. So, it is entirely done in the moving coordinate system. See, this zeta R 0 means what? Zeta R 0 is z minus V 0 t. So, you are differentiating with reference to moving coordinate. So, J 1 also has to be defined with reference to moving coordinate, and J 1 is the average flux over the entire cross section. So, that is what you are finding out here, 1 by pi R 0 square, that is. So, what you are doing again, annular area is 2 pi R dr, that you know, 2 pi R dr V into C, V into C into this area. Okay. Now, this since you are talking about the moving coordinate system, it has to be V z minus V 0. So, you are as if, I mean, your coordinate system is moving, and from that average location, what is the flux? Then coordinate system has moved here, but what is the flux? Then coordinate system has moved here, and what is the flux? So, that is exactly what you are doing, because your coordinate system itself is moving. You have already compressed that, you have already taken care of that radial part, you are working with the average concentration, and you are trying to find out how the average concentration changes with reference to zeta, mind it, not z, zeta is in moving coordinate system. So, any J1 bar, because of this convective flux, that J1 bar has to be calculated with reference to this moving coordinate system. So, that is how we have written here the J1 bar. Okay, so J1 is the average flux, and that is how we have written it here, and that J1 appears here. Now, you are doing, this is your modified governing equation. This is the modified governing equation that you are doing with C1 bar and J1. So, now you are solving this equation. So, to solve this equation, you have simplified this. Here you have written it in terms of tau and bring in this J1, put this here, solve this here and bring it there, and you will end up with this governing equation. And what you see basically here is, it is same as the one that you had earlier, only thing is, instead of diffusion coefficient you have this term V naught R naught by 48D. So, this you are calling as Ez, the dispersion coefficient, and you are proceeding with this as before. Now, we have talked about this circular cross section, that means we talked about a capillary here. We talked about a circular capillary. Now, if you do not have a circular one, instead if you have flow between two parallel plates, then in that case this 48 would be replaced by 210. I mean, people have already done this analysis. The stellar dispersion, this was originally done by Taylor, then it was modified by other researchers. They have done this entire exercise for flow between two parallel plates. So, not in a circular, not for circular cross section, and they found that this 48 becomes equal to the factor 210, and this R0 will be replaced by the distance between two plates. So, if somebody is working with a non-circular cross section, still there will be Taylor dispersion. Okay. Of course, I mean, it is the width, the dimensions, one has to be much higher than the other. I mean, when we talk about two parallel plates, flow between two parallel plates, the distance between two parallel plates is much smaller than the width of the channel. So, one is height, another is width. If I put it, then height must be much less than the width, and we are working with this. So you have the dispersion in the that between the two parallel plates. I mean, do you understand what I am trying to say? If you have two parallel plates, that means this is a plate, this is a plate, and this is another plate. This is another plate. So, you are having a flow through this. So, naturally, any parabolic distribution or any sort of distribution that will happen between these two plates. I mean, we are talking about, we are interested in this dimension. This dimension does not matter to us. Okay. So, this dimension, these distance between two parallel plates, that would be replaced by R0. That is what I am trying to say. Okay. If somebody is working with a non-circular one, then instead of R0, you will be replacing it by the distance between two parallel plates. Not of course, for a non-circular channel there is another dimension here, but that dimension would be inconsequential here for this purpose. All right. So, this is something which you need to be aware, that this 48 would be changed to 210 and R naught would be changed to distance between the parallel plates. If it is a square channel, it has to be figured out, somebody has to figure out. I mean, I am not aware of what should be the numbers or how it is to be, but that can be done. I mean, I am sure some researcher has already done it. I mean, it is just that I am not aware of it. Okay, so this is what we have as far as the this thing is concerned, as far as the diffusion is concerned, as far as the Taylor dispersion is concerned. The next topic that I pick up is the chromatography in a micro channel. Basically, if I look at what we have here in this PowerPoint slide, we describe solute transport in microscale chromatography. the objective of this is to identify components in gas or liquid mixture. That is what the main purpose here. What you look at here is the accumulation of a component. So, you are introducing a sample that has component A, B, C, D, and what you are looking at is the accumulation of a component. Accumulation of a component means either A or B or one of the components. Accumulation of a component at the interface between two phases such as the solid gas due to attractive intermolecular forces. So, accumulation of a component at the interface between two phases solid gas, where are you getting these two phases? So, you have a tube or you have a non-circular channel, and then you have the wall of the inner wall of the channel coated with an adsorbent material. Okay. So, some components, one of the components or maybe more than one components, they would accumulate at the interface, accumulate on the wall, that adsorbent layer that you put, that is a solid adsorbent. So, the interface between solid gas is at the wall. Okay. So, there the accumulation takes place, and this accumulation is due to attractive intermolecular forces. Now, if a pulse of a mixed solutes is injected into one end of a tube with inner wall coated with adsorbent, which is called a stationary phase in this context, then the solutes are adsorbed to different degrees and elute at different times. Solutes are adsorbed to different degrees and elute at different times. Now, the conventional chromatography utilizes packed bed. Microscale chromatography uses adsorbent coated inner walls of a channel or a monolith coated with adsorbent. All right. Why first of all, why something adsorbs, why something gets adsorbed on the wall, and why something will get dissolved also? I mean, because I am saying that a pulse of mixed solute is injected into one end of a tube with inner wall coated with adsorbent, that I am referring it as stationary phase, and then I am saying solutes are adsorbed to different degrees and elute at different times. So, I hope you, since we have a mixed crowd here, I hope you understand that there an adsorption and then a desorption, both the processes can happen simultaneously. What I mean by this is that in case of an adsorption, the flux of molecules moving from the gas phase to the solid phase, that is given as J1, which is proportional to C into 1 minus phi. What is C? C is the local concentration, C is the local concentration of that particular solute. So, if you are injecting the gas phase into this microchannel, then the local concentration of component A, which is being adsorbed in the gas phase, that is what is referred as C. And what is phi? This phi is fraction covered by adsorbed monolayer. Okay. So, what is this? So, you have a forward flux, this is called a forward flux. Similarly, there would be a backward flux which would be proportional to phi alone. That means, there would be a forward flux which we refer as adsorption, and the second one we can probably call this a desorption. So, there would be a forward flux, that forward flux means the flux of molecules from the gas phase to the solid phase. So, naturally that flux would be higher if you have higher number of component A present in the gas phase, and also the amount of coverage that has taken, because if the stationary phase, which is the solid adsorbent, if it is holding, it is because of intermolecular forces, it is holding the solid sample, the component A on the surface. If that surface is already covered, okay, if the surface is already covered, then there would be, I mean, so you will consider the surface to be completely saturated. So, there it cannot hold any more component A. So, how much remains unoccupied, that is important also. Okay. So, that is what is defining the forward flux. On the other hand, how much has been occupied, that is forcing a backward flux. Okay. It is forcing a desorption. So, there is an interplay between this adsorption and desorption, that you must understand. Okay. So, when you are putting a mixed solute, I mean you putting a pulse of A, B, C, D, depending, I mean now some are getting adsorbed more strongly, some are not getting adsorbed. So, you have a mixture of these components, you have A, B, C, D, and that is flowing through the channel. Some are getting adsorbed, and then what? So you have a concentration present. So, what you have done, you have given a pulse and that is flowing through the channel. Okay. So, this wall, it is seeing a high concentration of component A, which is supposed to be adsorbed. So, naturally that will be adsorbed, there will be huge forward flux and that would be adsorbed. Okay. And the pulse flows downstream, right. So, there is a pulse of this A, B, C, D, and then you are having a carrier fluid. So, that carrier fluid is pushing this pulse. I am talking about CARRIER. Okay. This case, it is typically an inert gas if for a gas phase system. So, this is pushing it down. So, once this pulse is gone, what will happen to this adsorbed layer? Then it will start desorption, right, because it is the C is not there. So, C is not for pushing the forward flux. So, there will be a backward flux. So, this is coming back to the system. So, you will be finding all these A, B, C, D, they are eluting, they are coming out at the outlet, but at different times depending on these dynamics of this adsorption desorption. So, that is the whole idea. Now, see, I said that here also you are resorting on a very thin channel, and so you would be having a very similar mass balance equation as you had in case of a Taylor dispersion. So, the mass balance equation, if you write the mass balance equation for mobile phase, what is the stationary phase? That solid adsorbent, and the mobile phase is that pulse that you have given, which contains A, B, C, D, carried downstream by the inert gas. So, that system you are referring as mobile phase. So, if you try to write down the equation, it would be something like this: del C1 del T, 1 is the species 1 we are talking about, out of A, B, C, D we are talking about, or out of species 1, 2, 3, 4 you are talking about species 1, you would be having, it is the first term is already known to you, the second term is a new thing we are talking about, an axial diffusion. If you are having a long channel, probably it is wise to have the axial diffusion also to be considered. Earlier, in case of a Taylor dispersion, what you have considered is basically the axial convection and radial diffusion. All right. Here, this is that axial convection term, this is the velocity term V del C del Z, that is that axial convection term, it is still there. Okay. Here, you have, this is the radial diffusion term, this is still there, d into this. Another term is additionally there, which was not additionally here, which is not there in the Taylor dispersion, is d del square C1 del Z square, this term. This is due to axial diffusion. Okay. So, this is the governing equation that researchers have considered for chromatography. However, this is only for the mobile phase. Okay, this is only for the mobile phase. What you have is another differential equation for the adsorbent phase. So, you are writing the second mass balance equation for the stationary phase, you call it, or you can call it for adsorbent. So, one for the mobile phase and other for the stationary phase. You are writing it here. What all you are considering here? Here, let me write the equation first. It would be del C1 prime del T. Why I am bringing a prime here? 1 is species 1. I have pulse containing 1, 2, 3, 4, I am talking about 1, species 1 here. Prime means the concentration inside the solid phase. So, that is why I am writing it as prime. This is equal to d prime by r del r of r del C1 prime del r. So, what you are considering here is only radial diffusion, no axial convection, because axial convection is not possible within a solid phase. Within a solid phase, axial convection is not possible. Okay. Axial conduction, that is, or you are talking about axial diffusion. Axial diffusion is not considered here, because there would be the concentration gradient in the axial direction within the adsorbent phase would be negligible. The concentration gradient of species within the adsorbent phase in the axial direction, that concentration gradient is negligible. So, axial diffusion is not important here. So, only thing that you consider is radial diffusion. Do you understand what kind of diffusion it would be? I mean, within the adsorbed medium. I mean, it is not not the kind of, I mean, the moment we say diffusion, what comes to our mind is that smoke diffusing. I mean, you have a small candle here and the smoke is diffusing in this medium, or you have a beaker full of water and you are putting a drop of ink, and that is diffusing. So, diffusion inside the solid, diffusion inside the solid. So, it would have a different kind of diffusion coefficient. But you must have already seen diffusion in catalyst. I mean, those who have I mean, any reaction, anybody who studied reaction engineering, you have a term diffusivity in catalyst. So, diffusion coefficient inside a porous solid is not something which is new to you, but one thing you must understand is that this diffusion coefficient would be probably order of magnitude different from a bulk diffusion coefficient in a liquid or in a gas. So, that has to be kept in mind. So, that is why in fact, I put this d prime. So, d prime is different. You can probably get a quick feel of this. This diffusivity is typically it would be the bulk diffusivity multiply, I mean, that means the diffusivity in a gas phase multiplied by the tortuosity factor. I mean, you have a porous network of this adsorbent that has a tortuosity factor that you have to multiply. So, it would be definitely, you know, that it will be an order of magnitude or more different. So, that is why you call it d prime. So, there would be only radial diffusion, axial diffusion, you know that concentration gradient is not important. So, that part is gone. So, this is the only mass balance equation that you have for the adsorbent phase. Now, if we try to look at the boundary conditions, then the boundary conditions for this one would be, for the mobile phase, boundary condition would be T is equal to 0, T is equal to 0, you have for all r, you have C1 is equal to m divided by pi r 0 square into delta z. You have given a small pulse at the inlet. So, this would be the C1, this is one condition, this you call it initial condition, and for t greater than 0 at r is equal to 0, symmetry has to be there. I mean, there is, you have not done anything. If you have a channel of circular cross section and if you have coated the wall uniformly, then you have no reason to believe that symmetry has been sacrificed. So, at r is equal to 0, del C1 del r would be equal to 0, that is known. And then you have another condition that at r is equal to r 0, that means at the wall at r is equal to r 0, you write there would be some continuity in concentration, and that continuity would be written as C1 prime is equal to H C1, that is one thing, and the other thing is d prime dC1 prime dr, that is equal to d dc1 dr. Do you understand? I mean, I'm talking. I will talk about this. This is people from chemical engineering background. This H is similar to the Henry's constant type term, but that is not. I mean, I will explain to you what is the basis for this H. But first, focus on this part. The d prime dc1 prime dr is equal to d dc1 dr. You got to understand the fact that whatever is arriving by radial diffusion, whatever is arriving by radial diffusion at the wall, that has to go into the solid phase. So, you have to have the continuity of flux maintained at the wall. At the wall, you have the adsorbent, and at the interface the continuity of flux has to be maintained. So, whatever is approaching the wall with a diffusive flux from gas phase side has to be equal to the diffusive flux that is penetrating into the solid phase. So, that is exactly what this boundary condition says. D prime dc1 dr, that is equal to d dc1 dr at r is equal to r0, that means at the wall. All right. So, this is one condition that you must appreciate. This one is by symmetry, you know we have not sacrificed the symmetry. This one is by that continuity of flux at the interface of adsorbent and the mobile phase. So, this is understood. And how do you explain this part? C1 prime is equal to H C1. If we go back to these expressions, one thing you can say is that at equilibrium, you will write J1 is equal to J2. Okay. And if you write J1 is equal to J2, you would be writing then, now you will have a constant, because you know that though we have written these expressions, I have to have a constant term here, and that constant term is defining which species will be adsorbed more and which species will be adsorbed less. Okay. So, if for J1 is equal to J2, you can write, if you equate these two, we would be end up with phi is equal to C divided by K2 by K1 plus C. That means that layer that is being, the fraction that is covered, that is equal to C divided by K2 plus K2 by K1 plus C. This is what you will end up with. Okay. So, what you are assuming here is that the concentration in the solid phase is equal to, it depends on the concentration in the gas phase in a linear manner. That means, there exists a linearity between these two concentrations. I mean, it may be, it is an assumption, you are making an assumption, but the objective of this is to one good reason for taking this assumption is that people have come up with an analytical, the researchers have come up with an analytical expression for this whole system of equations. That means, you have one equation for the moving phase, another equation for the stationary phase, and with these boundary, I mean, I have not talked about the boundary condition for the solid phase yet. We are still in the boundary condition in the moving phase. And so, for this combined form of equations, people have the researchers have come up with an analytical expression very similar to the one we had done for Taylor dispersion. So, by accounting this linearity here. Okay. And the reason for this linearity I can see here is that at equilibrium I can have this phi is equal to C divided by this quantity. All right. So, depending on this value, depending on these value, you can come up, you can have these the linearity established. Okay. So, this is what you have here. Now, if I try to write quickly the boundary conditions for the solid phase, what you have for the solid phase is at t is equal to 0 for all r, C1 prime is equal to 0 for all r. C1 prime is equal to 0 and t greater than 0, r is equal to r plus delta del C1 prime del z is equal to 0, del C1 prime del r is equal to 0, where you have del C1 prime del r is equal to 0 and delta is equal to the thickness of adsorbent layer. This delta is equal to the thickness of the adsorbent layer. So, at the end of the adsorbent layer, no diffusive flux is possible. So, that is one boundary condition you have, and at t is equal to 0, adsorbed layer is completely it is just a native layer, nothing has penetrated into it. So, this is the boundary condition that you have there. So, you have a mass balance equation for the adsorbent phase with some boundary condition, you have a mass balance equation for the mobile phase with some boundary condition, and then these the researchers have come up with a solution, in fact analytical solution numerical is still a possibility, but analytical solution is available, and the advantage of this is then if you can express it in a similar manner and come up with an Ez term, then you can probably see the effect of various parameters on the Ez term. That is good. Then you can get a feel for these terms, how they influence the spreading of this front or spreading of this pulse in a microscale in a microchannel in a chromatographic system operating in a microchannel. So, we will get to the final expression and the importance of various terms. This time with the it is not possible for getting into detailed derivation. I will just give you the final form and the importance of various terms in the next class. That is all for today.